I will begin with a word of prayer. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless this class, Lord. In him I pray. Amen. Okay, so today I will finally share with you some of the toys that I have discovered for A-Calculus. I mean, so let's get started here. A definition. So today is about the A-Cauchy-Riemann equations. And so the basic theorem that we're going to work with is this. If f, which is, from some domain of an algebra to the algebra, so we got as a function, and f is real differentiable. Oh, that's not even what I want. Excuse me. Continuously differentiable. At P in the domain of F, okay? Well, I guess my grammar is not awesome here. If F is a function which, I should, instead of saying and, which is continuously differentiable at P in the domain of F, and here's where I wanted the and satisfies dfp of x times y equals to dfp of x times y for all x, y in A, then, punchline, f is an element of the a-differentiable functions at P. So, I mean, to be a little bit pickier, this is fine. That means that there exists an open set around the point P on which f is a-differentiable. Continuously differentiable means that, the partial derivatives of the function, of the component functions of f exist and are continuous. The algebraic condition I just wrote down is what we're going to define to be the Cauchy-Riemann equations. This, in fact, write a linear of the differential. This right here, in fact, is, in my view, this is the Cauchy-Riemann equations. All right, now that's not how we'll often look at them, but I think that's kind of the most rudimentary, basic form of the equations. Yeah.
I probably missed something. Is this different from that one that we talked about?
Well, so let's see here. There's two worlds that I'm talking about, right? The one world is, let's see here. So we have ACR equations and continuously differentiable, right? Actually, we could just talk about ACR equations and real differentiable. These two things paired together well, stink, I'm sorry. I do want continuously differentiable. That is a theorem that gives me that it's a-differentiable. If I have that the function is a-differentiable, then we talked about last class, a-differentiable ability of the function implies, this is last class. One of the things I talked about last class was that if we have an a-differentiable function, it's automatically real differentiable and its differential satisfies this boxed equation. Now I'm saying we can go the other way. If we have continuously differentiable, then there's a theorem that says continuously differentiable implies real differentiable. So, but real differentiable is a pain to check. Continuously differentiable is easy. That means we just have to see that the component functions are continuous, right? We don't ever actually work that out. We just like look at them and go, polynomials, exponentials, sines, cosines, continuous, yay, great, go on. And so, but real differentiable and A-Cauchy-Riemann equations, those two things holding, that is essentially the definition of a differentiable. So this is the interrelation. But this is the theorem we're working with. So if we satisfy the A-Cauchy-Riemann equations, and we have this continuous differentiability of the function, then we get that it's a differentiable. Which then means we have all that calculus we looked at last time: sum rule, product rule, chain rule, all that good stuff, right? Okay, so what I want to talk to you about today is how can we understand the Cauchy-Riemann equations? What do they actually look like for specific examples? And what's the best way of unraveling the red boxed equation, really? Yeah.
Can you just say again what the CA?
Oh, this is my definition for functions on A which are a-differentiable in some open set containing P. So you've got like the point P, and there has to exist some kind of like open ball around that. And for every point in that open ball, the function is a-differentiable in that open ball. The interesting thing is the Cauchy-Riemann equations holding at P paired with the continuity of the partial derivative means it suffices to check that the Cauchy-Riemann equations hold at P. Like the continuity kind of smears out the result past that. All right, so it suffices to check the Cauchy-Riemann equations at that point. Okay, anyway, that's all right. So the theorem. We are, of course, not content to leave it at that. Actually, I've got a couple of examples before the theorem, and I probably should stick with my plan, which was to show you these examples, because I think they help. If we have f equals to u plus iv, all right, then the Jacobian of f is ux, vx, uy, vy, right? That's the Jacobian, 2 by 2 matrix. If we had that, if we had that df of, let's say, zw at some point p was equal to df at point P of z times w, right? If this condition held for all z and w, what does that say about the Jacobian matrix? Then what can we say about the Jacobian matrix of f at the point P? It should be an element of what? The matrix representation of the complexes, right? This is one of the things we learned, that there's an equivalence between the right linearity of the differential and its matrix being in the regular representation of the algebra. What does this mean for complex numbers? Okay, for complex numbers, this means that, so there exists, let's say, a plus ib in the complexes such that what? The Jacobian of f, right, at the point P is equal to the matrix representation, the complex matrix representation of a plus ib, right? What does that mean, though? Specifically, that means that the matrix ux, vx, uy, vy, right, that Jacobian matrix has to be equal to, what's the matrix representation of A plus IB? Remember, we've seen this a few times. You got your A, you got your B, minus B, A, right? So if these two things are equal, what does this suggest about the partial derivatives of the complex function f? Right, see, exactly. So from A, we can see that ux equals to vy, and I mean, A is equal to that, actually. B is equal to what? It's equal to Vx, right? Which is equal to minus Uy. These things I just wrote, and I'll put a box around them, these guys right here, these are the standard Cauchy-Riemann equations that you learn in complex analysis. Okay? So the theorem that I just stated, I could restate as follows. If, so here's that theorem for just complex analysis. Theorem. If U and V are continuously differentiable, at P, then, and Ux equals to Vy and Vx equals to minus Uy at P, then f equals to u plus iv is a function which is complex differentiable near P. The converse is actually not true. It's possible that the function could be complex differentiable at P, and yet, oh, wait a minute, I'm an idiot. Well, let's not talk about the converse till later. We have more toys to play with, but you might worry that you don't have continuous differentiability at the moment. Certainly you get differentiability, but continuous differentiability is a stronger condition than differentiability. There are functions which are differentiable in the real sense, but not continuously differentiable. Let's not, that's like third order discussion in here. Let's not get into that at the moment. So anyway, those are the Cauchy-Riemann equations, and there you have it for the complexes. All right, so what about the hyperbolics? What do they look like for hyperbolics? If we have f equals to u plus jv, then we have the Jacobian of f is, again, ux, vx, uy, vy, and that should be equal to the matrix representation in the hyperbolic, for the hyperbolic number, a plus bj, for some, if we have the differential at p in the regular representation of the hyperbolics, right? Well, I'm sorry, more to the point, dfp of vw. So if we had that the differential of this hyperbolic function satisfied the A-Cauchy-Riemann equations in the sense that it's right linear, then what does that say about the partial derivatives of that function? Well, this is what? This is A, B, B, A, right? That's the fundamental representation of the hyperbolic number A plus Bj, as we've discussed. And so we get A is ux, which is equal to vy, and B is equal to vx, which is equal to uy. And so there you go. These, which I'll box in blue here momentarily, these are the, the hyperbolic Cauchy-Riemann equations. I mean, if you'd like, we could come up with a different name for these different things. I mean, technically, it's a different thing, right? The thing I boxed and read at the start of lecture, if you want me to be precise, it's the right linearity, the right alinearity of the differential, right? Oftentimes, when people talk about Cauchy-Riemann equations, they're talking about the things I just boxed, actual specific scalar equations which relate to the partial derivatives of the components of the function. Okay? So this game I'm playing, right, of just matching like basically pattern matching of the Jacobian matrix against the regular representation. This is how I thought about Cauchy-Riemann equations to start with. Like the first, I don't know, half year I was working on this stuff, this is how I thought about it. And it gets you a long ways, but eventually you figure out that there's a better way of looking at it, and that's what I want to share with you now. So this is my, let's say, more, I guess, grown-up way of looking at the Cauchy-Riemann equations. This is my theorem. Well, let me put it over here. Theorem 6.25. And so, again, we have A equals to Rn, all right? And F is, let's suppose F is a differentiable near P. Then a couple things. Number one, we could say that partial F partial xi times ej is equal to the sum over k of cijk, yuck, of partial f partial xk, where you might wonder what the cijk's are. Well, the cijk is as follows. Ei times ej is equal to the sum over k of cijk ek. This defines the cijk. These are the so-called structure constants of the algebra. So you could write the Cauchy-Riemann equations in terms of the structure constants like this. I almost never do that for you guys in here. I don't think this is a productive viewpoint for us. Point two is actually very productive in the dominant way I look at the Cauchy-Riemann equations in this course. If E1 is the identity in the algebra, we find partial f partial xj is equal to partial f partial x1 times ej, for j equals to 2, 3, n. And those, in fact, are the Cauchy-Riemann equations. Those are logically equivalent to the boxed right A linearity. This is actually if and only if. If those equations are true, then the differential is right linear and vice versa. Assuming the differential exists, you have that theorem, yeah? And then 3. So I would say 2 for me is the standard Cauchy. For me, that's actually my standard Cauchy-Riemann equations, what I just wrote down. Those ones, that's how I think about it. 3 is for commutative A. We have these really nice symmetric Cauchy-Riemann equations as follows. Partial f partial xi times ej is equal to is equal to, well, it doesn't matter, it's symmetric, right? So partial f partial xj times ei, but we could write it as ei times partial f partial xj. Since it's commutative, you could go either way. These are, in fact, equivalent conditions. If you assume one, you can get any of the others. They're just really a different notation for the same algebra. I'm going to just prove, maybe I'll just prove 2 for you guys here. So what I want to show for you, I want to show you that 2 follows from the right linearity. Let's see how, okay? So let's assume that f is, a differentiable at P, near P, right? Then we have that dfp is in the regular representation of A, which, as we know, implies that dfp of x times y is equal to dfp of x times y, right? We have this right A linearity of the differential. Okay? Now, another bit of calculus that I need to share with you, I've shared with it, I think I've told you guys this before, but if you haven't had advanced calculus and you haven't thought about calculus in Rn that much, maybe this hasn't popped out at you, but the partial derivative is related to the differential with respect to, let's say, xj, is dfp P of EJ is in fact equal to partial f partial xj. So at the point P, to be careful. So the relation between the differential and partial derivatives is just this. If we take the differential and we act on EJ, that gives us partial f partial xj. For those of you who've had linear algebra, this makes perfect sense because the jth column of the standard matrix of the differential is what? It is partial f partial xj, right? So how do we construct jf? How was it? Partial f partial x1, right? Da-da-da. Partial f partial xj for the jth column. But what is this? This is the standard matrix of df, right? At the point P. Fine, there's p's everywhere here, but don't make me write them, please. So my point is that's what how we connect the partial derivative with the differential. We just act on the standard. That's it. Okay? That's the connection. So to prove 2, we just look at, let's see here, partial f partial xj at the point P is going to be df P of EJ, right? But this EJ is in the algebra A, right? So we can write EJ as 1 times EJ, right? 1 times EJ. One times EJ. And then we use the assumed right linearity of the differential. We can pull EJ out to the right. And what do we got? dfp of 1 times EJ, right? But what was 1 equal to? Or by assumption here in part 2. We assumed that 1, the identity for the algebra, was also E1. Often the case, our algebras, our examples that we look at, that is the case. That's the case for our standard nomenclature for hyperbolic numbers, for dual numbers, for n-dual numbers, for n-hyperbolic numbers, for complex numbers, for complicated numbers. All of these things have the identity as E1. All right? The only example I think I shared with you guys where that's not the case is the direct product, R with R, where we had the identity be 1, 1, which would be 1 plus E2, right? So this 2 does not apply to the direct product algebra. Okay? There's that. That's true. But this is E1, which means that that is nothing more than partial f partial x1 at the point P times EJ, which is what we set out to prove. That is equation 2. In my view, the most convenient form of the Cauchy-Riemann equations. You're like, well, if it's so convenient, how would your second example look like in this new formalism? Let's look at example 2. I guess this is example 2, right? This would be example 1. Yeah? For the sake of discussion. So example 2, E1 is 1, right? And E2 is what? Listen, look at me. I said E2. I wrote EJ. What's wrong with me? But E2 is J. Yeah. So what does 2 look like? Partial f partial y is equal to partial f partial x times j. That's the Cauchy-Riemann equation. Now it's a vector equation. A vector equation in the hyperbolic numbers is 2 scalar equations. What is this? This is uy plus j vy is equal to ux plus j vx times j. Multiply by the j, what do you get? You get vx plus j ux. For a hyperbolic equation to true, it has to match the real and also the imaginary component. Patent pending. So this has to match that, and this has to match that. Those are exactly the hyperbolic Cauchy-Riemann equations I wrote just a second before in this lecture. in similar beautiful fashion, we can rewrite the complex Cauchy-Riemann equations as what? So over here, the viewpoint 2 looks like what? It looks like partial f partial y is equal to partial f partial x times I, right? But this is uy plus ivy is equal to ux plus ivx times I. Multiply through the I, we've got minus vx plus iux. And as you can see, this matches that, this guy matches that guy. Those are the standard Cauchy-Riemann equations for the complex numbers. But the efficiency of viewpoint 2, I can't overemphasize the efficiency of viewpoint 2. Now, part 3 is proved by a very similar calculation. Like the proof of part 3, you can almost see from what I wrote down. I'll let you look at the notes. The proof of part 1 is technical, but who cares? I mean, I don't even use 1 in here, but I would state it for your reference, because some people like to think about the generalized Cauchy-Riemann equations like this. By the way, a lot of times people say the A-Cauchy-Riemann equations are the generalized Cauchy-Riemann equations because Cauchy-Riemann is just the complex case. That's the first thing that was done. This hypercomplex analysis I'm sharing with you was only discovered later, like the late 19th century. It seems like maybe 1890 to 1920 is where the heyday of this stuff was. But, all right, so there you go. That's important. So how many Cauchy-Riemann? Yeah.
So in your theorem where you state the complexes and then your general theorem 6.25, they seem to be the conditional conditions pointing in the opposite direction. Is that potentially?
What I'm trying to, really all I'm trying to say with theorem 6.25 is that right linearity, okay, is equivalent to these conditions.
All right.
So if you marry this idea, if you also have continuous differentiability of the function paired with any one of these 3 algebraic conditions, lets that theorem take over and give you a differentiability at P. And so, but yeah, admittedly, I haven't stated this theorem in a very logically clear way. I admit it. Maybe I should just say, probably a better preamble to this would be let A be, the algebra, and let F be a function which is real differentiable. I think that's, well, yeah. Let me try for a better statement. All right, let's say it this way. And F is real differentiable at P. Right? The following are equivalent. And then maybe part 0 would be that dFP of V times W is equal to dFP of V times W. I mean, that may be a better way for me to communicate what I'm trying to communicate here. Fair enough. I appreciate this kind of feedback because, I'm still wrestling with these ideas and working on the best formulation of these theorems. Yeah. So, okay. Listen, yep.
So if you had like more than 2 bases.
Let's get to that, yes. What if there were more than 2? Yes.
Okay, so like the 2 that you did, that was just E1 and E2.
Right.
You only have
What if, yeah, so
one and, like,
give me a 3-dimensional example. What's a 3-dimensional example that we like? The 3 hyperbolics. Example 3, I like it. H3. So we're talking about things of the form A plus BJ plus CJ squared, such that A, B, C are real numbers, right? And J cubed is 1. The 3 hyperbolic numbers, right? In this case, E1 is 1, E2 is J, and E3 is J squared. So theorem 2 applies. How many Cauchy-Riemann equations do we have? So we'd have partial f partial y is equal to, well, j times partial f partial x, right? And we'd have partial f partial z is j squared times partial f partial x. And these would be your, H3 CR equations. In components, this looks like uy plus jvy plus j squared wy. Here I'm letting f equal to u plus jv plus j squared w like I did in your homework, yeah? That nomenclature again. And so like the partial derivative of f with respect to y is uy plus jvy plus j squared wy. And that would be equal to, j times ux plus jvx plus j squared wx, like so. And then if you multiply this out, you get, well, wx plus jux plus j squared vx. And so we get three scalar equations from that. So in terms of scalar equations, how many Cauchy-Riemann equations are there for the three hyperbolic numbers? Here's three of them. Yeah, uy equal to wx. You've got vy equal to ux. You've got wy equal to vx. You could look at it like this, right? You could go back to the pattern matching. We got ux, we got vx, we got wx, we've got uy, we got vy, we got wy, we got uz, we got vz, we got wz. This is the Jacobian matrix of an arbitrary three-dimensional function, a function on R3, right? And that has to match the regular representation of the three hyperbolic numbers, which we know is a, b, c, c, a, b, b, c, what'd I do, a? Okay. And let's see here. So like uy equal to wx is actually coming from what? Uy is this one, right? So these are equal. So we've already discovered the uy equals to wx. There's also a equal to vz, yeah. And looking at b, we got b is b, right? Which means that this and this and this have to be equal for an H3 differentiable function, which was vy. Oh, that's the third equation. Vx is equal to wy, which is equal to uz. Yeah. And the other one, I need another marker. So like, of course, this. That pattern has to match up, right? And so, well, that's what I've already got. Vy equal to ux. We also have vy is equal to wz. So there you go. I mean, there are actually 6 Cauchy-Riemann equations for the three hyperbolic numbers. And by the way, you could look at this as the matrix representation of partial f partial x, yeah? By the way. So does that start to answer your question?
So then if you did the same thing as the top partial, like where you set the equations equal, you did the same thing to the bottom, you just get the other half.
Yeah, we get these other 3 from this condition. Or you could look at it as pattern matching. I don't recommend the pattern matching way. I think this way is like way better. Okay. All right? Way, way better. So because, okay, so we've defined the first derivative, right? You can also define a second derivative in the same way you do in Calculus 1. So the derivative of a function on A is another function on A which we called f prime, right? So what would f prime prime be? It's just the derivative of the derivative function. So we just define differentiation, higher differentiation iteratively in the same way as usual. And quite beautiful things happen for higher derivatives. I'll show you. So like, if we had, if we could, so definition f prime prime of p is going to be f prime prime of p. Okay, I mean, that's, all right. In other words, you differentiate the derivative to get higher derivatives and so forth. Now, I don't want to get dragged into let's see here, how to say this. If I'm not careful, this can spin into like a 30-minute discussion, right? And I don't want to do that right now. I just want to give you the main takeaway from this other realm of thinking, because it's really, really neat. So essentially, the point is this. So long story short, we have that f prime is partial f partial x, right? For E1 equal to the identity. So actually, f prime prime ends up just being partial squared f partial x squared. And generally, the kth derivative in the sense of A-Calculus is just the kth derivative of the first coordinate, just like that. But there's more. If your function is, if you have a smooth, so this is the theorem. If f from A to A is real smooth, in the sense of being smooth in the real sense, I mean, what I'm trying to say is it has real derivatives, which can be iterated. So the partial derivatives exist and are continuous at all possible orders. Like I can take second, third, fourth, however many derivatives you want, all day long, continuous. So if it's real smooth, and f is once a differentiable, then f is infinitely a differentiable. So once a differentiable implies infinitely a differentiable in the backdrop of assuming that the function is real smooth. So in other words, we can calculate the upteenth billion algebra derivative of it, and a formula for calculating it actually wrote before the theorem. But there's more. There's more. Also, and this is where it's really just shockingly cool, the kth derivative of f with respect to partial xi1, partial xi2, partial xik, guess what? That's equal to the kth derivative of f with respect to the first variable times vi1 times vi2 times vik. Now, part of the reason I'm reluctant to go through the proof right now of this for you is that we're going to discover an analogous theorem for complex functions as we soon focus merely on the complex case in here, right? So this, in some sense, is a a foreshadowing of a more specific result I'm going to derive for you guys as we go forward. But I do need to share it with you right now because I think it will help you appreciate why I care about A-calculus a little bit more. If we look at just, let's see here. So let me look at this theorem. Specific application. Let's look at partial squared f partial y squared. A equals to the complex numbers. Partial squared f partial y squared. Yep.
Where it says the partial of x to 1, is that an h or is that
That's a k.
no?
I think it's n, right?
Or
No, they're k's.
Or no, the denominator.
oh, okay.
That's a k. It's all k's. K, 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 K. Oh, wait a minute.
You don't say that 3 times.
See here. Oh, I just thought of something that I would definitely have to edit out. All right, so partial squared f, partial x squared. And if I follow this theorem, like I'm in the complex case, right? So I'm saying this is x2, x2. So I'm supposed to do times e2, which is right. So times I, right? And we just use juxtaposition in the complex case. So what does this say? Partial squared f partial y squared is equal to minus partial squared f partial x squared. In other words, fxx plus fyy equals to 0. I don't know if you know this or not, but this means uxx plus ivxx plus uyy plus ivyy equals to 0, which gives me that uxx plus uyy equal to 0, and also vxx plus vyy equal to 0. What are these equations I just boxed? What are these called? I don't know. These are Laplace equations. So the component functions of a complex differentiable function necessarily solve the Laplace equations. You might ask, okay, so if a complex differentiable function satisfies the Laplace equation, then what would like a hyperbolic differentiable function satisfy? Hyperbolic differentiable, right? Then we'd have partial squared f partial y squared equals to partial squared f partial x squared times j, right? Which would then give me uxx minus vyy equal to 0, and I'm sorry, that's supposed to be u, and vxx minus vyy equal to 0. These are the so-called wave equations, where really we're thinking of one of the coordinates as being time and the other one space. You've probably seen a wave equation like second partial derivative with respect to time is proportional to the second partial derivative with respect to space. This is the transverse wave equation. Actually, you probably haven't seen it. Although Comportus will sometimes cover this in Physics 1, which you might have had. Those are the quote-unquote Laplace equations for the hyperbolic calculus. There is also, there's always a second order of, there's second order differential equations which are necessary consequences of the Cauchy-Riemann equations. For the 3 hyperbolic numbers, the game is simply this, guys. You can basically, let me just sort of cut through the noise here. What I'm saying is that if you can write down an equation that's true for the algebra, it translates into a corresponding partial differential equation for the component functions. So what equations can we write that are quadratic for the 3 hyperbolic numbers? I'll get us started. We can write things like 1 times 1 is equal to, let's see here, how about j times j squared, right? So this is like an x, this is like an x, this is like a y, this is like a z. This says that fxx is going to be equal to fyz for the three hyperbolic numbers. That's actually the import of this theorem. Any equation you can write down amongst the generators of the algebra corresponds to a partial differential equation which must be satisfied by the components of the functions which are differentiable. Now this is interesting to me because A-Calculus has got all kinds of nice properties. So it seems to me, if I can take a system of partial differential equations, right, and I can look at it and understand how it's actually, let's say, the Laplace equations for the algebra in disguise, that means maybe I have a hope of taking that problem in partial differential equations and like translating it into a problem of calculus over the algebra, which I can solve then with just ordinary like kind of Calc 1 and Calc 2 kind of stuff. This is my larger program of thinking, which I'm still working on. But anyway, I think these, I mean, this to me was shocking when I found it. I was like, it's that simple? Holy cow. So like Laplace's equation really is just coming from the fact that 1 plus I squared is equal to 0 in the complex numbers. This 1 squared translates into, fxx plus fyy equals to 0 in view of the theorem I wrote over there. That's it. Now, you typically see this derived in a much more circuitous fashion in the complex course, all right? So I think I was thinking I had till 1, which is incorrect, isn't it? So I have just enough time to get in trouble. Let me project something for you. So this is not the, okay, so I just thought, it occurred to me I should talk about this viewpoint, the higher order problem as well today, because I think it's part of the same story, right? But there's another way of looking at the Cauchy-Riemann equations, which is also interesting and especially important for us in complex analysis, which is the z-bar viewpoint, complex conjugation, right? So is there an analog of complex conjugation, and what does, is there a conjugation of the algebra? So we're sorry, I think to tease you, Sam, but I mean, I'm going to say something about it today. I'm at least going to put it on the board, but we're not going to do it justice today. And I guess we're not going to do it justice Friday either. Stupid hurricane. I can make a video. Whose idea was that? Let the record show. It was Nick's idea that I make a video. I will do that for you, Nick. Thank you. I wasn't planning on it until you said that just now, so thank you.
Sorry guys, I'm aware.
That's a lie. I was already planning, but it's more fun to blame Nick, right? I don't know. I really want to say these things to you guys in person. Partly I don't want to make a video because I really want to talk to you guys about what I'm about to talk about in person, but what? So, long story short, this is you can define not one conjugate, but j conjugates like this. And this is, I'm going to share with you the result, which is that the Cauchy-Riemann equations can be recast with these new, so here's what it looks like for the complex case. For the complex case, if you look at z and z bar as we have before, then formally you introduce this partial z bar and this partial z bar. These are the so-called Wirtinger's calculus. So for him, partial z bar is this partial derivative, linear combination of partial derivatives in x and y, and that linear combination of derivatives in x and y for partial z. And when you sort through it, when you write down, what does it mean if you calculate partial z bar with respect to the barred coordinate? Well, when you put in the Cauchy-Riemann equations we just learned, out pops 0. So if it's complex differentiable, partial z bar is 0 if you define partial z bar like this. And on the other hand, partial z, if you have a complex differentiable function, it's just partial x. So in other words, partial z is df dz, or f prime as we've been denoting it. All right? And the Cauchy-Riemann equations just become, yet another way to look at them, partial z bar is 0. Okay? What I discovered about 2 summers ago is a way to generalize this I think. Well, I was building off another researcher, but I think theirs was wrong a little bit. And because it had some, well, it just wasn't, it was close, but it was just not quite right. And I generalized the typical formal rule, and I introduced partial derivatives with respect to an invertible basis on the algebra, like so. Here's my partial zeta, my partial zeta bar k. There's not one of them, but there's n minus one of them because we're in an n-dimensional algebra, so there's more than one conjugate. And with respect to these partial derivatives, you can say that, in fact, if the function is a-differentiable, then f prime is nothing more than partial f partial zeta. And then the Cauchy-Riemann equations become the vanishing of all the conjugate derivatives. Partial zeta bar 2, partial zeta bar 3, da-da-da, partial zeta bar n. So that you have n minus 1 conjugate derivatives vanishing. Those are the Cauchy-Riemann equations. That's yet another viewpoint. So what I'll do in the video is try to wrap this up, and then when we come back from the hurricane, we will hopefully be on to just complex. So like after the hurricane, I'm going to try to just be talking about complex calculus. Mission, what are we on? 3, I will hopefully conjure up. That will have a lot of A-calculus because that's what we've been doing, right? But I'm about to do a hard segue. When you get to chapter 7, there's almost no A-calculus. It's just back to my complex notes. And so like test 1 is going to be up through chapter 7 in the notes. So like a lot of that, it's not all A-calculus. It's a mixture. But anyway, I shut up. Enjoy the hurricane, I guess. I don't know. What am I supposed to say at this point? But there is some chance that the power will go out before I get your video posted, right? So.